Hi and welcome back to maths class. In the previous video we looked at some applications of integration. We looked at average value of a function. In this video we're looking at motion in a straight line as an application of integration. So before we get started, I just want to remind you about some things that we already know about motion in a straight line. Specifically that x, which is the position of a particle, is a function of t, which is time. So their v then we found was dx dt, the derivative of the position function. And then acceleration is dv dt, which is the derivative of the velocity function. So that means if we can differentiate x to get v and differentiate v to get a, then it follows that we can anti-differentiate a to get v and anti-differentiate v to get x. And that's what you see there. X is the antiderivative of v of t dt, and v is the antiderivative of a of t dt. But that's not all that we can do with motion in a straight line problems. So the next thing we want to look at is the distance travelled. Now, the distance travelled is not the same thing as the position, all right? But we have to be really careful about this because this assumes that we haven't changed direction, all right? So in fact, I should pop that in. Okay, there it is. It assumes no change of direction. So we can be traveling in one direction and our velocity is changing, but if we're not changing direction, then this is going to give us the total distance traveled. Now, if we had changes of direction, we would have to do this more carefully. But for now, this is what we've got. If we start at time t1 and we finish at time t2, and we take the definite integral of that interval of v of t dt, then that will tell us how far we've gone. So it doesn't give us an x function, it doesn't tell us where we are, it only tells us how far we've gone, all right? Now, if I've got a distance travelled and I divide it by the time taken to travel there, then you know that that is going to give me the velocity. Okay, but this is an average value. This is not the velocity function. This is an average value. So if I start at a certain point at time t1 and I finish at another point at time t2, then the average velocity is going to be the time taken, 1 over the time taken, that's t2 minus t1. And then to find the distance travelled, I will find that definite integral. Now notice that that looks very, very similar to the average value of a function, and that's because that is the same formula, but instead of a and b, I've got t1 and t2. So that's average value of a formula, average velocity. Okay, so we need to do some worked examples to see how this all looks. So here's our first worked example, and it looks a bit familiar because we've done problems like this before in differentiation, but now what we've got are some new tools to help us to solve these problems. So a stone is projected vertically upwards from the top of a building 20 meters high. Don't try this at home, kids, with an initial velocity of 15 meters per second. This example is actually out of your textbooks. It's one of the worked examples, but it's the one I'm going to go through. So we will assume that acceleration due to gravity is negative 10 meters per second. That should be squared. So negative 10 meters per second squared. And we need to find various things. The time taken for the stone to reach its maximum height, the maximum height reached by the stone, the time taken for the stone to reach the ground, and the velocity of the stone as it hits the ground. So we'll get started first of all by working out all the equations that we need. And the main bit of information that we want to start with is that we know one function because we know that acceleration is only due to gravity, so it's constant. So I can write down that acceleration equals negative 10 because that's what I'm told. That means I can anti-differentiate acceleration to get velocity. So that's going to give me negative 10t plus c. And so now I'm going to go back to the question and look for some more information to help me find c. The initial velocity, I'm told, is 15 meters per second. So when t is 0, the velocity is 15. So c must be 15. So the velocity is negative 10t plus 15. Okay, I am going to need to find an actual height. So that means that I need to anti-differentiate again. So x is going to be the integral of this function above here, negative 10t plus 15 dt, which gives me negative 5t squared plus 15t plus another value of c. But before I put that in, let's look back at the question. I'm told that it is at the top of a building 20 meters high. So if I'm taking 0 as being ground level, then my initial location, that is when t equals 0, is 20. So instead of writing c here, I'm just going to go ahead and put 20 straight in there. Okay, so now I've got these equations here, one here and one here that I can use. And so I'm now going to start answering the questions. Find the time taken for the stone to reach its maximum height. Now that's not necessarily an immediately easy thing to do. And what we might be tempted to do is look at that word maximum and think, okay, I need to find the maximum height. I need to differentiate something and make it equal to 0. And we could go down that path. But let's just think about the situation. When the stone goes up in the air, and then, sorry, you can't see that. When it goes up in the air and then it stops and starts coming down, that maximum height was when it's went up and started coming down again. So basically the maximum height is going to be when the velocity equals 0. So when the velocity equals 0, I get 0 equals negative 10t plus 15 and t equals 3 over 2. Okay, part B. I need to find that maximum height. So now what I need to do is substitute in the value I've just found for t into the x function, which gives me the location. All right, so now I have substituted in, and I quickly wrote down 3 over 2. I rewrote it as 1.5. I didn't want to start squaring that fraction. And I used my calculator to do this. So I've got negative 5 times 1.5 squared plus 15 times 1.5 plus 20, which comes out to 31.25. And what I went back also and did was I popped in my units there. T is in seconds and x is in meters. And I know that because of all the units that I'm given in the question are in meters and in seconds. Okay, part C, the time taken for the stone to reach the ground. Once again, I need to interpret the question. The time taken for the stone to reach the ground. Well, when the stone reaches the ground, that's going to happen when x equals 0. So what I'm going to do now is I'm going to take the x function and I'm going to make it equal to 0 and I'm going to solve that. And it's a quadratic, so I'm hoping that it will factorize nicely. So let's have a look at it. Well, I've got a factor of 5 and I'm going to take it out a factor of negative 5. That's going to give me t squared minus 3t minus 4. Get rid of that. So I'm going to have negative 4 and 1. T minus 4 and t plus 1. So if that equals 0, then that's going to give me the solutions of t equals negative 1 and t equals 4. But t is time. So t must be positive. So t equals 4. Just checking that you can see that. Oh, not quite. Hang on, let's see if I can move it. There we go, but now we can't see the whole question. Anyway, you can see there that I've written so t equals 4, and I'm just going to pop that back over. Okay, the last part of the question is to find the velocity of the stone as it hits the ground. So I know that that happens when t equals 4. So now I'm going to go back to my velocity function and just substitute in. I'll do that over here. Part D, when t equals 4. That's when the stone hits the ground. So V is going to equal negative 10 times 4 plus 15, which gives me a grand total of negative 25. And that's going to be meters per second. Now, just a comment on some interpretation here. Negative 25, the velocity is negative because the stone is now traveling down. So the initial velocity that I was told in the question, you can't see it now, but let's just show it to you. The initial velocity was 15 meters per second, and it did say vertically upwards. So we take up to be positive and down to be negative. And that's why our acceleration was negative, because acceleration due to gravity is always pulling us down towards the earth. So in all of these, if I needed to interpret my answers, t is always since the moment I threw the stone. So t is always going to be positive. In this example, x is always going to be positive because I took 0 as being the ground. I could have defined 0 as the starting point, in which case it would have hit the ground at a negative distance. But it's much easier to just make 0 be the ground every time. And then my velocity can be up or down, so either positive or negative. And in this question, the velocity was constant. Okay, so that is my example of motion in a straight line. There are other examples, but this is the only one I'm going through today.